In this session we are going to apply what we learned so far in a larger example. The task is to develop a square root function using Newton's method. That's the first time that we need more than a couple of lines to actually express a program, and we will learn new techniques and new tools for doing so. So what that means is that we want to define a function with this signature. It takes a double, it gives me back a double, and the return value is the square root of its parameter x. The classical way to compute that is by successive approximations using the method of Isaac Newton. So let's see what this method is. To compute square root of x, we start with an initial estimate value. It doesn't really matter what that estimate is as long as it's positive, so let's pick y equals 1. And then we repeatedly improve the estimate by taking the mean of the old estimate y and the value of x divided by y, where x is the value we want to draw the root from. So let's see that in action. So the value of x in our example would be 2. Our initial estimation is 1 as usual, so the initial quotient is 2 divided by 1, that's 2, the mean is 1.5. Now we plug in 1.5 to our estimation, we get a new quotient of 1.33, a new mean that you see here, and you see that it converges very quickly to the actual value of 2. So now we have an abstract algorithm. Let's see how we would put that into a function that computes that algorithm. A typical way to code algorithms in functional languages is to go step by step. So we take a small task and formulate it as a function, and then probably that task will need further tasks that then would be defined in their own function. The first function we want to define is the actual iteration, called that square root iter, which says, well, if we have a guess and the value we want to draw the root from, what do we do? Well, either we stop the iteration and return a result, or we go and do another iteration step. The predicate that controls that, we give it a name. Let's call it is good enough. So if my guess is good enough, then I just can return the guess. If my guess is not yet good enough, then I have to improve my guess. Let's do that with another function, improve, and call square root iter again with the improved guess. Note that square root iter is recursive, so its right-hand side calls itself. One peculiarity in Scala is that the return type of a recursive function needs to be given always, whereas for other functions it's optional. The reason for that is that to compute that return type, the Scala compiler would have to look at the right-hand side, and because the square root iter function is recursive, it's stuck in a cycle. It would need the return type for that to compute the type for the expression. To break the cycle, we require that recursive functions always have explicit return types. It actually makes sense even for other publicly used functions to give an explicit return type, because that's good documentation, but it's not required by the language. Okay, so let's implement this in practice. What we're going to see is a new way to write programs. So far we have done everything in the REPL. Now for larger programs we have something that's better adapted. We go into Eclipse and we start a worksheet. So I take you through the steps one by one. Here we have an empty Eclipse thing. We first start a new project, a Scala project. Call it, demands a name, call it ProgFun for the course. And then in the project, what we can do is define a package, which is essentially a directory, in which we are going to put all the stuff from this week. Call this week 1. You don't need to define packages, but it's good practice to keep stuff tidy and ordered. And then in that package, we define a new sheet. It needs a name. Let's call it session. In a worksheet, what we can do is we can type expressions and have them evaluated just like in a REPL. So we can do 1 plus 2, and expressions get reevaluated when we hit save. That would be Command S or Control S. But the expressions show up on the right in a different column that you see here. We can also define functions, let's say the absolute function that we've seen before. So we could say, well, if x is less than 0, minus x, else x. And the REPL would answer with the value of the absolute function. Well, not the wrapper of the worksheet, but the two are actually quite related. It's just a different mode of presentation. One thing we can do, which is nicer in the worksheet, is we can actually go back and edit expressions, and the re-evaluation will then show the edited value. So it's not just a single line editing window, but a whole window that we can use. So let's use the worksheet to complete our square root function. The first thing I'm going to do is take it from the slide. So I select square root iter here and paste it inside the worksheet. I can reformat with Ctrl-Shift-F, so that would format things nicely. But the worksheet still doesn't compile because, of course, I have two functions here that I haven't yet defined. That would be isGoodEnough and improve. So for isGoodEnough, let's do that first. So isGoodEnough takes these same parameters as square root iter, and it returns a boolean that says whether we can stop the iteration or whether we need more steps. So what could that predicate be? Well, one way to do it would be to say, well, if we take the current guess here and we square it, if we're close enough to the original value x, then guess by itself would be close enough to the desired square root value. So let's code that up. This would say guess times guess minus x. We would have to take the absolute value of that. And it would have to be smaller than some epsilon value, let's say 001 for the moment. Okay, so that was number one. The second function we need to define is improve. And that's now the core of the Newton method. We would say, well, to take a guess and an x, and to improve the guess, what do we do? Well, we say we need to take the mean of the value of the current value of guess and the quotient of x divided by guess. So to take the average, we would first sum the two values and then divide by 2. Good. Now we have a worksheet that compiles. You see here on the right hand side, you see all the types. The last function we need to define is square root itself. So let's do that. What would that be? Well, it would be the square root iteration. With our first initial value, we said that was 1.0 and x. Well, now we have all the elements in place and we can start to test our function. Let's start with square root of 2. And we get 1.4142, so that looks right. Let's do another one, square root of 4. And we get something close to 2 as we would expect. So as an exercise, I would like you to think about the implementation we have so far and try to improve it. One thing to improve is that the isGoodEnough test is not very precise for small numbers, and it can lead to non-termination for very large numbers. So here let me demonstrate that. Let's take a very small number, let's say 1 to the minus 6, so 1 over a million. So our square root, the square root we would expect to see is 1 over minus 3, and actually what we see is 0.03, so that's pretty far away from where we want to be. And the other problem we have is if we take a large one, let's say 1 to the 60th power, what would we see then? And actually what we see is non-termination. You see this here with this little bar. It says, well, it doesn't find the square root. Not so good. Let me take that out with an escape. So can you explain why that is? Why is the isGoodEnough test not precise for small numbers, and why can it lead to non-termination for very large numbers? And secondly, can you define a different version of isGoodEnough that doesn't have these problems? Here are some numbers to test your version, some very small and some very large numbers. So to answer that exercise, let's go back to our worksheet. The problem we had for both small numbers and large numbers was that our is-good-enough test takes an absolute difference. It asks whether the absolute difference between the square of guess and x is less than some threshold value. And that's not very good for very, very small numbers, because the number we want to find in the square root might even be smaller than that. So that, relatively speaking, that epsilon value might be huge compared to the number we want to find. And for very large numbers, we have the opposite problem, which is that very large floating point numbers can actually be further apart than this epsilon value. That means in the 52 bits they have available for the mantissa, it could be that the distance between one number and the next is actually larger than 0.001. And in that case, of course, the iteration can never stop, simply because there is no value that's ever good enough. So we can solve both problems by making the test proportional to x. And that's very simply done by saying, okay, let's divide the absolute difference by the current value of x, and let's make that be smaller than the threshold value. So once I've done that, I can simply re-evaluate my spreadsheet, and now I will see that everything computes nicely. And for the small number, I get something very close to 1 to e minus 3 as expected. And for the large number, I get something like 1 to e30, and that's also as expected.